All right, conceptual questions. All right, we're going to do the next few pages. With this unit, there's a lot of conceptual questions and, looking at stuff, writing. Unfortunately, there's not a lot of application because, well, quite frankly, we can't experiment with nuclear bombs. That's out of our jurisdiction. So we'll have to talk about it instead. So with that being said, let's go over the next, I want to say 19 questions or so, something like that. All right, number one, which of the following are nucleons? So this one's pretty straightforward. Protons, neutrons, or electrons. When you think nucleons, think of things like in the nucleus, which we talked about earlier, right? Two of these things which have mass are in the nucleus. And that is the protons and the neutrons. Protons and neutrons. Those both have mass. More importantly, they're both in the nucleus. That's where they reside, right? Okay, some of these I'm going to write, by the way. Some of them I'm just going to say, so yeah. All right, number two. How does the number of electrons in a neutral atom compare with the number of protons in its nucleus? So this is very important. So very important is this. This is good consider. So first of all, electrons, negative. Protons, positive, right? So that should give you a hint right here. What is the atom they're talking about? Neutral. Neutral means even, right? So how does the number of electrons compare to the number of protons in a neutral atom? Well, your answer should be something along the lines of the number of electrons equal the number of protons. Which makes sense, right? Because electrons and protons should be even, which means the atom should be neutral, right? Because if one of them has, if there's a misbalance, then it's going to have a positive or negative charge. Okay. Number three. What is the principal role of neutrons in a nucleus? Okay, so with this, it's going to kind of be a loose answer, and I'd like you guys to find this and kind of word it your own way. But I'm going to say to act as a sort of like nuclear cement to hold the nucleus together. Right? So it helps stabilize and hold the nucleus together. But I encourage you guys to find it and reword that yourself so you can understand that. All right, number four. So we just did this one. Number four. Between what kinds of particles does the nuclear strong force act? So it acts between and we just covered this, the nucleons. What are the nucleons? Protons and neutrons. So that's where the nuclear strong force interacts, right? Okay, number five. Which force has a longer range, electric force or strong force? So those are two forces, right? So this is the electric force. Bam. Okie dokie, let's keep going. How does the presence of neutrons help keep the protons from pushing apart from each other? So, this is another one where I'm gonna talk to you about the answer, but I want you to find it, and that way you can sort of formulate it and shape it in your head. 'Cause sometimes some things are hard to get unless you see a few definitions of them, see a few examples, and that way your mind can like put it together. Right? So the answer I'm going to give you is, so we're on number 6. When neutrons are present, the attractive strong force is increased relative to the repulsive electric force. Right? So it increases the attractive strong force in an atom relative to the repulsive, meaning separating electric force. So that's number 6. Bam. Alright, So let's talk about 7. Distinguish between alpha, beta, and gamma radiation. So distinguish means pretty much tell me what they are, and that will help us distinguish. So alpha is positive electrical charge. Positive electric charge. Beta is negative, right? And gamma is electrically neutral. So that distinguishes these 3. Alpha positive, beta negative, gamma is electrically neutral, right? Okie dokie. Number 8. Now I want to say there is a picture in your text showing number 8, penetrating power. So check that out. Even after this answer, check it out because it's a good picture because it kind of helps illustrate the point. So first of all, penetrating power. Penetrate means like to push past or push into, right? So penetrating power of the 3 kinds of radiation. So the 3 kinds, well, that's what we just talked about, right? Alpha, beta, gamma. So alpha can be stopped easily by a piece of paper. So alpha has the least penetrating power. So alpha stopped by 2 P's there, paper. Pretty easily, right? Beta. Beta can be stopped by several sheets of foil, right? Stopped by a few sheets of foil, several sheets of foil. And when I say foil, I mean aluminum foil. And this is, just to give you an example, we're talking about, usually this refers to like density of material. So it's not like foil happens to be stronger, because foil is kind of weak, but it is very dense, right? That's why when, you go to the dentist or you go somewhere and you get an x-ray, usually they'll make you put on a lead vest. The reason they use lead is because it's super, super dense. So it stops that kind of radiation. So what's the last one? Gamma. Gamma. Gamma is very difficult to stop. And like we just talked about, it's blocked by lead or very heavy shielding, right? Blocked by lead. Lead is very dense. Very dense. Your pencil is not made of lead. Your pencil is made of graphite, I believe. Should be. So keep that in mind. So don't hide behind a pencil if there's like a nuclear bomb. You will get incinerated. Alright, so again, alpha, blocked by paper. Beta is blocked by a few sheets of foil. So just something enough to block it. And then gamma is, it has a lot of penetrating power, so you'd have to be behind something super dense and thick like lead, right? Okay, number 9, distinguish between an ion and an isotope. You may want to Google isotope. You may want to Google them both. Just Google stuff, okay? So, I think we talked about isotope earlier. We're going to cover them both. So we have ion and we have isotope. So, ion, to give you the definition, it is a charged particle. What does that mean? That means it has a different number of electrons. What's the charge of an electron? You remember? It's negative, right? So if you have extra electrons, you're going to be negative. If you are missing the normal amount of electrons, you're going to be positive, right? So when they say different number of electrons, means it's an atom that is positive or negative. That's an ion. It is not neutral. Okay? A neutral atom is not an ion, right? So it has extra electrons, meaning it's negative. In that case, it would be called a anion, I believe. I don't know if I spelled this right, but anion, whatever, YOLO, anion. We'll go with that. If it is positive, meaning it's missing electrons and it's a POS, positive, it is called a cation, I believe, and I don't remember if I'm spelling that right, but sound it out. So, ion equals a charged particle, either positive or negative. That's easy. Isotope. We talked about isotope when we did the vocab, but isotopes have a different number of neutrons. Different number of neutrons. When you guys do this, write stuff out, don't abbreviate. I'm abbreviating, please don't abbreviate. Give me a few more words, it's not very hard. So, first of all, what's the charge of a neutron? You remember that? Hopefully you do. Neutron equals, well, it isn't negative because electrons are negative, right? Neutrons are neutral. So having a different number of neutrons is not going to affect the charge of an atom. It is going to affect the mass, though. Remember, because they do have a mass. So, ion is a charged element. Isotope is an element with a different number of neutrons, right? How we talked about the example of a person carrying an apple, carrying a basket of apples. So maybe their normal apples they carry is 10 apples. Well, if they have a different amount of apples, let's say like 8 or 16, instead of their normal 10, well, they're an isotope, right? They themselves aren't any different, but they do have a different mass because they're carrying more or less apples. So, there's the first set of conceptual questions. Awesome job. Let's move on to the second. Let's recalibrate. I think this one, from what I remember, is a lot about fission. I don't remember if we talked about fusion, but I know it's a lot about fission. It's definitely a little bit deeper. So, here we go. Number 1. What is the role of electrical forces in nuclear fission? When you do these, if you're reading in the book, don't be bashful about getting online and seeing if you can find a different definition. It's never a bad thing to try to look up multiple explanations of something, because the more angles you hit something, the more it helps you understand. Because sometimes you can find a definition and maybe for you it just doesn't work, you know? Or you can find somebody that explains something and maybe they're the best explainer in the world, but it just doesn't work for you. You know, I remember trying to learn electricity a little while back, a long time ago. And I remember taking, physics in college and high school, and nothing that any teacher would ever say helped me understand electricity. I just couldn't get it because it's something that I couldn't really visualize. And I had a buddy that actually became a teacher down the road, and this was when I was like 27, well after college and high school, and he explained it, and for whatever reason, his explanation just stuck. I was like, oh, well, that makes perfect sense. So sometimes it's just the person explaining it, and there's nothing wrong with, having different people explain. Some people work well, and, you'll get it. It's like a silver bullet. It just penetrates, and you got it. And, some explanations just don't. So, again, don't feel shy to look in other places. All right, here we go. Number 1. What's the role of electrical forces in nuclear fusion? So, for number 1, if the nucleus is stretched into an elongated shape, we're talking about nuclear, hopefully I didn't say fusion, it's fission. So fission is splitting apart, right? If you remember that from the definition. Fission equals splitting. So if a nucleus is stretched into an elongated shape, the electrical forces may increase the elongation and overwhelm the nuclear strong force until the nucleus splits. So, think about it like this. You got two forces at play. You have a force coming in, and you have a force going out, right? So from the definition we just talked about, electrical forces spread out, electrical forces, and nuclear strong force goes in. Now, if you can, and I think we'll talk about this later, or actually I know we will, but if you can elongate it, you can get it to, you can make there be a like a misbalance, we'll say, to where one force, the spreading out force, beats the coming together force. Like if you stretch a rubber band enough, you can stretch it a little bit and there's kind of a balance, but once you stretch it a certain amount, that stretching force will beat that pulling together force and you'll have a snap. And when it does snap and break, what happens? It pops your fingers, right? Well, it's the same concept where it releases energy, except for instead of popping your fingers being the energy, it incinerates cities, right? It's a lot more energy. All right, let's look at number 2. What is the role of a neutron in nuclear fission? They say that's on page 630. The information page numbers change from time to time. Hopefully it's still 630 when you guys are reading it. But the role of a neutron, and I think you'll see a graphic on this, is it starts the fission process. So remember, fission is the splitting, right? So think of you stretch a rubber band, so the forces are the element is really elongated, right? You throw a neutron at it, and that's what causes that rubber band to initially start splitting. And once it splits, it releases that energy. So our answer is a neutron starts the fission process. So starts the fission process. Okay, cool. So that's what a neutron does. Number 3, what happens to neutrons that are produced when a nucleus undergoes fission? So in other words, it's elongated, fission starts to happen, bam. When it does happen, it releases some nucleus, or excuse me, I'm sorry, it releases some neutrons, bam. Those are NEU, neutrons, NEU. So they're saying, yo, what happens to these neutrons that get released or get produced? These neutrons can cause fissioning of more nuclei. What does that mean? That means it is a chain reaction. So you throw a neutron at this first one. It splits, undergoes fission. It releases 2 more neutrons. Well, these 2 more neutrons cause more fission. So, in other words, 1 releases 2 neutrons, which cause more fission between 2, which means they release 2. NEU, NEU. So see how this process is getting bigger and bigger? See how it's like a chain reaction? Like if I was to give you $1 every day, and the next day I gave you let's see, $1 for every dollar that you had. So day 1 I give you $1. The next day I give you one more dollar, right? And then the next day I give you $1 for each dollar. So then I give you 2. And it grows and grows and grows, and pretty much in a month you'll have like $1 million, right? So convert those dollars into energy, and you can see how there would be a lot of energy released. So number 4, why does a chain reaction not occur in uranium ore? So the answer is uranium ore is mostly uranium-238. So it's mostly uranium-238. And the thing about uranium-238 is it absorbs neutrons without fissioning. So anything you throw at it, it just absorbs it. So therefore, fission's not going to occur, right? So there you go. So it's mostly this uranium. You throw a neutron at it, and it's like, cool, give me that neutron. Next. And so there's no, it doesn't use that to release any energy, right? So it just absorbs it. All right, number 5. What is critical mass? So critical mass is the amount of mass for which each fission event produces, on average, 1 additional fission event. So what does that mean? That means for every fission event, anytime this happens, fission happens, it's the amount of mass that's going to get produced on average. So when you think mass, think of neutrons and what neutrons getting released and so forth, right? So it's the amount of mass that's going to get produced from this reaction. Okay, so there we go. And look these up if you want a better definition or a different one. Look them up online. No worries. Bam. Let's go up. All right. So number 6. How long did it take for scientists and engineers to extract enough radioactive uranium to make the Hiroshima bomb? So, in other words, you got to get a certain type of uranium, collect enough to make a bomb. So it's not like you just get one atom of uranium somewhere and you're like, boom, I've got a bomb. I'm ready to go. No, you've got to get a lot. And there's a long process for collecting that uranium. So we're saying, yo, how long did it take to get enough to make this bomb? So it actually took more than 2 years. It took them more than 2 years to collect enough. That's greater than, by the way. That's not 70, even though it looks like a 70. Greater than 2 years. It took them over 2 years to collect enough radioactive uranium to make a bomb, right? Okay. Number 7. What is released when heavy atoms split into nuclei of lower atomic number? Well, that one's pretty simple and straightforward. Energy. Atoms split. Remember how we talked about earlier, like the atom is defined by its atomic number, its number of protons. So if you split helium, for example, I believe helium is number 2. You split it, you're going to have hydrogen and hydrogen, right? Because that's 1 and 1. You're splitting 2 to 1 and 1. So when you split these really heavy atoms, you are going to release energy, and a lot of it. And when there's a chain reaction, you're going to release a lot of it, right? Number 8. What's the difference between fission and fusion? So, this one's pretty straightforward. Fission. Fusion. I got a dry throat. Okay. So, usually with me, I can remember one of them, and then I just know the other one's the opposite of the first one. So, let's do fusion first. Fusion, oh, I always mess that up. It's only got one S. Fusion. Fusion is like fusing bones together, or like fusing metal together. Fusion, light nuclei fuse together. Light nuclei fuse together. You take a couple light atoms, fuse them together. Nucleus. Awesome. Fission. Heavy. Nuclei. Split. Apart. Pretty simple, pretty straightforward, right? Fission, they split apart. Obviously, they've got to be heavy to have enough stuff to split apart. Light, fusion, they fuse together. It's pretty straightforward. All right, number 9. After fusion, the total mass of the nuclei formed in the fusion process is blank the total mass of the nuclei that fused. So after fusion, after things come together, the total mass of the nuclei formed in the fusion process is less than the total mass of the nuclei fused. All right. After fusion, the total mass of the nuclei formed when it fuses together is less than the total mass of the nuclei that fused. Cool. There we go. Number 10. Why are we currently unable to produce energy using fusion reactions? Okay. So I'm not going to write this one down, even though it's not a long sentence. I just don't want to write it. But you write it down. So why can't we use fusion, so fusion coming together to produce energy in a reaction, right? So the answer is temperatures necessary to produce fusion reactions, they're too high. It's hard to deal with that stuff. So when you think about stars, why they glow, why they release energy, that's because fusion's happening in stars. And obviously temperature is getting really high, right? I mean, the star's glowing, it's releasing tons of energy. And all that gravity is smashing elements together. So, why can't we produce energy using fusion reactions? because temperature is just the temperature necessary to make that happen has got to be like very, very high. It's got to be high. So it's hard to deal with that, and that's why we do not do it. Something I do want to kind of touch on, because this can be a little confusing for number 9. So after fusion, the total mass of the thing that formed is less than the total mass of the nuclei that fused. So let's say we fuse a 5 and a 5 together, smash, and then we get equal 9. And then you're like, well, that doesn't make sense. We fused a 5 and a 5. Why are we getting 9? That's because some of that mass, a very small amount of it, gets converted to energy. And that's why there is a lot of energy released. I mean, if you convert a very, very tiny bit of energy into, and I'll try to put a video on this, into a mass into energy, it releases a ton of energy, right? So you don't have to do much. There's a video, and I'll see if I can find it and put it on, but they talk about if you could convert your whole body directly into energy, like boom, convert it into energy. Like how much energy would that be? What kind of damage would that do? And I want to say it's a pretty crazy amount. I can't remember off the top of my head how much, but it's a crazy amount, right? So sum up number 9, 5 plus 5 equals 9, and that 1 goes off in the form of energy. And a lot. So those are your conceptual questions. I think that's the last of them. So there you go. If you guys got any questions, please let me know, and don't hesitate to cross-reference or check any of these.